It's the middle of the night, but I don't keep respectable hours, and I haven't for some time now. So let's talk about double integrals over rectangular regions. This is a picture that I drew in one of my notebooks, and I did use a diagram in Calculus by Briggs as a reference when drawing this. I just wasn't going to attempt to redraw this with my mouse because I'm just not. Um, but all it's trying to show is that we are using rectangular solids to approximate a volume in a volume for some three-dimensional shape in 3 space. This is our three-dimensional shape, right? And in calculus 2, in 2 space, and in calculus 1 in 2 space, we used to use Riemann sums to try and approximate an area underneath a curve. This is the same sort of idea, but instead of rectangles, we're going to use rectangular solids because we're doing this in 3 space. So one thing to note is as n approaches infinity, delta approaches 0. And up here, z is equal to f of x and y. These things are the same, right? And z is the roof of this thing. So is the roof of this thing. And this is the region that we're trying to approximate. So this is the volume in limit summation form. So it says the limit as delta approaches 0 for the summation, where the index is 1 all the way up to some number n for f of x sub k and y sub k, integration with respect to a sub k. And here delta represents the maximum length of a diagonal of the diagonals of the rectangles as and then as delta approaches 0, the number of elements in the partition start to approach infinity or some higher number, right? And so the reason that this is shown in summation form is because limit summation form, because it's like if you pull back the curtain on calculus 3, if you pull back the curtain, this is all limits, and this is all summations going on behind the scenes. So we could put it in integral form, and we can say that we have the double integral of f of x and y dA, and that equals exactly this, what we just said. And one thing to note is that delta a sub k, and this is really just dA. And then also these asterisks here, I think these are just placeholders. They don't really have a meaning, like, but ostensibly they're supposed to mean that it's like a placeholder. Like they could be raised to some power, right? That's at least how I interpret that's at least how I interpret it. But it's saying that the function is a function of x and y, which is why it's multivariable. But I like to think of these asterisks as just like little placeholders. So but altogether, x sub k and y sub k with these asterisks, they're at the endpoints of the partition. So if you were to partition this thing up, these are the endpoints in the partition. This gives us the net volume of the solid bounded by z equaling f of x and y over the region R in the xy plane. So this here is like the full flex, right? This is the full flex, but this is what we are going to be working with primarily. Okay, and so here I just tried to draw like an image that just shows like I tried to draw an image showing some rectangular solid, some three-dimensional thing. I mean, this is a rectangular regions. We're doing rectangular regions in this section with this roof, this purple roof, and this purple roof is f of x and y, which is also known as z. All right, so yeah, cool stuff. It's good to get a visual. It's good to see the sort of more complex formulas, but then realize that this is what we're going to be working with, and this is a lot nicer. I mean, they're both nice. They're both pretty. They're both aesthetically pleasing. I like both of them, but one of them looks a little bit less intimidating. So this is called, I think this is called a Fubini integral. It's an Italian guy, I'm pretty sure. Fubini. This is Fubini's theorem. He was alive in 1907, so around that time. Shout out Fubini. Thank you for this theorem. So essentially, what it says is that if we let f of x and y be continuous on a region, then that region is shown here. That is x x and y, you can describe that as a being less than or equal to x, which is less than or equal to b. In other words, x is in between a and b. And c is less than or equal to y, and y is less than or equal to d. In other words, y is in between c and d. And so if we want to like think about this graphically, we can invite our old friends x and y, and we can mark it up. We can say that let's see, look, one here, one here, one there, and one there. And we could say, okay, well, this is A, and this is B, and well, this is C, and this is D. So if I know that X is going to be between A and B, then X is going to be between these here, right? Between A and B along the x-axis. And if I know that y is going to be in between C and D, that means it's going to be in between here, right along the y-axis. And so if that's true, then I'm going to have a region that looks something like this. And that's going to be what the region is bounded in between. And so the double integral of f of x and y over R is given, so that's the region over this, is given by the following. And so what this is showing is it's showing that we have the double integral, and both of these integrals, let's just look at this one first. Both of these integrals have limits of integration. And we see that it's the double integral. The first one is the integral from c to d times the integral from a to b of f of x and y, integration with respect to x and integration with respect to y. Now, what this equation is showing is that, you know, you can flip the integrals so long as if I flip these, then like this is one integral in of itself, right? And so if I'm gonna change the integration order, then I need to make sure that the corresponding dy or dx also gets flipped, because it's a set; these go together. And also you want to be careful and kind of eyeball it, because um, a lot of the times one of the integrals are a lot easier. One of the combinations of the integrals are a lot easier to solve than the other one. And so we'll get into that in a second. When it comes down to solving these integrals, when you have a double integral, you want to evaluate the inside integral first. You start at the inside and then you work your way out. So if this is a function, I would evaluate this first, then I would take the result of that and apply this integram with these bounds of integration and integrate with respect to this variable. So let's do an example. This says that it wants me to evaluate the definite integral from 1 to 3 times the definite integral from 0 to 2 for x squared times y, integration with respect to x and integration with respect to y. So let's jump right in and let's look at this. With this here, I need to do the inside integral first, and the outside integral has a dx in it. So that just means that the y gets treated as a constant and that I can factor it out. But the first thing that I want to maybe do actually before I jump in is I'm just gonna rewrite this. So I'm going to evaluate what's in red first. And because this is integration with respect to x, y gets treated as a constant. So I really can just factor that out. So I'm going to take that y and I'm going to pull it out. Okay, and now I'm going to evaluate what's the integral of x squared integration with respect to x. Well, we know this is going to be a power rule situation, so we're going to do that. And well, with that, I'm going to have y times x raised to the third power over 3 because it's a power rule situation. But as for the bounds of integration, I'm going to put x equals 0 and x equals 2. And then on the outside, I'm going to put dy because this is all taking place within the integrand. So notice that this dx and dy are different. This is integration with respect to x, this is integration with respect to y. So when I'm evaluating the bounds here, I'm going to say, okay, x equals 0 and x equals 2. And that's a good habit to get into when you're doing multivariable calculus integrals. So now at this point, I'm just going to keep working through this. I'm going to evaluate this at the bounds of integrations via the fundamental theorem of calculus. And so I'm just going to jump in. And well, for the upper limit of integration, it's 2. So I'm going to have 2 raised to the third power over 3. And then from that, I'm going to subtract the lower limit of integration. So that's 0 raised to the power of 3 over 3. And I'm going to bring in that dy. So this is all taking place inside of the integrand of this integral here. That is the integral from 1 to 3. So inside of the integrand, I'm going to have what 2 times 2 is 4 times 2 is 8, 8 over 3. So, and this is going to go to 0, right? That's going to go to 0. Oop. I don't really have much room out there. Like this. This is going to go to 0. 0. So then inside of the integrand, I'm going to have 8 times y over 3. And this is going to have a dy on the end there. So now with this, I can evaluate this integral. I know how to do that. So what I'm gonna do is I'm gonna factor out the constant, factor out 8 over 3, and I'm gonna multiply that times the integral from 0. I'm gonna factor out that 8 over 3, and then I'm gonna multiply that to the integral from 1 to 3 of y, integration with respect to y. And so with that, I'm going to have 8 over 3 times y squared over 2, because the power rule gets applied. And then as for the limits of integration, it's going to be, for the lower one, y equals 1, and it's going to be y equals 3 for the upper limit of integration. And I'm just going to evaluate this like normal. I'm going to do 8 over 3 times 3 raised to the second power over 2 minus 1 raised to the second power over 2. And, well, that's going to be 8 over 3 times 9 halves minus 1 half. And, let's see here. 8 over 3 times 8 halves. That's going to give us 64 over 6. 64 over 6. So what do I do? To try to simplify this thing, I'm going to break it in half, because they're both divisible by 2. They're both divisible by 2. And so 64 divided by 2 is 32. And 6 divided by 2 is 3. And so the answer to this is going to be 32 thirds. So that means that the surface, the surface here, and the surface here, let's look at our formula right here. And maybe I should note again that z equals f of x and y, right? So that means that here, z equals, in the integrand, x squared times y. And so what that means is that the surface z equals x squared times y describes the ceiling, and the region is the xy plane. Dx came first. Dx came first, so x went from 0 to 2, and then y came second, so y went from 1 to 3. So r in this case describes the surface over the top of it, and we just found the volume. So so let's see here. We're going to do our xy plane. And well, we did x first. X went from 0 to 2. Maybe like this. And then y went from 1 to 3. 1 to 3. And so then the region in question here, we'll do this in blue. If it went from if x went from, so the region in question here, it's like this, right? And so R describes the surface over the top of this and we just found the volume. So R describes the surface over the top of it, and we just found the volume. So the surface is x squared times y, and that describes the ceiling of the region. And that's in the xy plane, and that's this. But what we just found is we found the volume. We found the area in this 3-dimensional space, but this in the 2-dimensional space here is the roof of that, and this is the volume. I need to grab my formula. Oh yeah, everything's crashing right now. That's all right. I'm gonna keep going. The world around me burns as I do mathematics. Okay, all systems are crashing, but let's keep going. So this says to evaluate the double integral with region R, with the integrand being y times Euler's number raised to the power of x and y, dA, and this is taking place on the region that is R equaling R equals the region, so it's going to be x and y is the region described, and x is going to be between 0 and 1, and y is going to be between 0 and the natural logarithm of 2. And so here, let's look at this, and let's see how this is going to help us. How is this thing going to help us? Yeah, let's just look at this one here, right? dA, basically dA gets written down when we don't know which integral we want to come first. We're given the bounds of integration, so that's taken care of. But we don't know which integral do we want to come first. Like, which one do we want to come first? So if I want to work out an integral with a dA in it, it's up to us to describe which integral we want to come first. So note that the region that they're giving me right here, it shows that x is going to be in between 0 and 1. And then y is going to be between 0 and the natural logarithm of 2. So the region in question here, it's going to be right here. And the surface is the surface above this, the surface above it is y times e raised to the power of x times y. So there's two different ways that I could do this. I could do this with the dx first, or I could do it with the dy first. I have two options. So let's look at option 1. So I'm going to set up my bounds of integration. And then I'm going to draw in my second integral. And these are my bounds of integration. And then the integrand stays the same. Y times Euler's number raised to the power of x times y. But instead of writing integration with respect to a, well, we wrote in the y's bounds of integration first. And so 0 to 1 is with respect to x, because it's the x bounds of integration. So we're going to have dx dy. But there's another way we could do it. right? There's another way we could do it. Our second option is going to be like this. Right? I'm flipping the integrals, and I'm flipping the dy dx. I guess I'm flipping dx dy in this context here, but this is my second option. Okay, so I have two options how I want to do this. So, uh, we have two possible integrals. One of them requires integration by parts, and one of them requires u substitution. Well, I'm going to go the u substitution route because it's u substitution. But you could solve this with integration by parts as well. So this is u sub. This is integration by parts. So the inner first. I'm going to solve this with u substitution. U sub, then I can set what equal to what? I think u becomes x and y, and let's see, well, the original integrand here, this is dx. So when I go to find my du, well, that constraint is still honored in that y gets treated as a constant. And so when we take its derivative, we're really just gonna make x a focal point because y gets treated as a constant. So the derivative of x is 1, and then we did the constant multiple rule with y, so we're going to multiply y times 1, and so we're going to be left with y dx, I think. And maybe I can show the steps just because I don't want to be gatekeepy to people who are watching, and who maybe don't know how to do this stuff in your head. So basically what I just did is I was like, okay, well, I want du, and well, we're taking the derivative with respect to x for x and y. And there's a y in there, but the y is going to get treated as a constant, and we're taking it with respect to x. So that means that du equals y times the derivative of x. And I need more room here, but the derivative of x is 1. And so we're going to end up with see, du equals 1 times y. And well, 1 times y is y, and also there's gonna have a dx. And so now we have to evaluate this at its upper bounds and its lower bounds. So I'm actually gonna bring this over here. So I do need to do my upper and my lower bounds. So let's see here. Let's see for our upper bound. What's our new upper bound gonna be? The new upper bound is gonna be well, u is x and y, and upper bound is 1. And we're gonna plug in for x, so it's gonna be y, right? Because here x equals 1, and well, u is equal to x times y, which means that it's equal to 1 times y, and 1 times y is y. So that's our new upper bound. The lower bound can be found in a similar fashion. This is lower bound. Lower bound. And so, well, in the lower bound, well, x equals 0, and u equals x and y. Well, and then that's going to be 0 is going to get plugged in. So 0 times y, anything times 0 is 0, so it's going to be 0. And so we'll rewrite the integral with our u sub. The integral from 0 to the natural logarithm of 2 times the integral from 0 to 1 for y times e raised to the power of x times y, integration with respect to x, and then integration with respect to y. And so if we apply our u substitution, this is going to become the following. That is, the definite integral from 0 to the natural logarithm of 2, that stays the same. We're leaving that alone. We're just evaluating the inside. We'll do this in blue because we wrote out our u substitution in blue. So earlier I said we wanted to factor out that y. We actually don't want to factor out that y because we need that y because we have the y is in the integrand and that equals du. And so when we set up the u substitution, we're going to have the integral from 0 to natural logarithm of 2. It's going to be times the integral from the new bounds of integration, which is 0 to y for what we set u equal to, which is x and y. So we have e is raised to the power of x and y. Well, now e is raised to the power of u, and then so putting that y back in the integrand. I don't even know why I wrote that. This was my mistake. We're gonna leave it like this because we need it like that. We need it like that because we want that y dx, right? Y dx and the y dx equal to du. So now we can integrate this. E raised to the power of u is can be integrated fairly easily. So e raised to the power of u, integration with respect to u, and on the end of that, we're going to have dy. Now integrating e raised to the power of u, e raised to the power of u is so unfazed and so unbothered by literally everything because if you do e raised to the power of u, e raised to the power of a variable, so long as there's no constant in it, in front of that variable as a coefficient, it's just going to be e raised to the power of that same variable. So what I'm trying to say is, and goes both ways for anti-differentiation and differentiation, but basically what I'm trying to say is e raised to the power of x integration with respect to x equals e raised to the power of x, but since this is an indefinite integral, we're going to put it plus c so we don't leave a trail of mistakes on my digital footprint, because that's mathematically technically the right way to do it. But what I'm trying to say is that well, this is going to be the definite integral from 0 to the natural logarithm of 2 times, well, we're going to integrate that now. So it's going to be e raised to the power of u evaluated from x equals, well, I guess in this case u equals 0 and also u equals y in integration with respect to y. And so we're gonna need some more room to take this thing on. All right, so let's play because this is gonna be the integral from 0 to the natural logarithm of 2, and we're gonna apply the fundamental theorem of calculus. So that's gonna be e raised to the power of y minus e raised to the power of 0, and anything raised to the power of 0 is just 1. This is gonna be dy. So what are we gonna have? Integral from 0 to the natural logarithm of 2. This is going to be e raised to the power of y minus 1 integration with respect to y. Now this is a little bit easier to work with because this is going to be a linearity rule situation, and I'll write it out, but look, I mean, we're going to integrate that e raised to the power of y, and then integrate that minus 1. Well, the 1, it's just going to have a y on it, so it's going to be e raised to the power of y minus y, I think. And then we'll evaluate that at the bounds of integration. But I'll write it out. So what is this going to turn into? Well, e raised to the power of y is unbothered. So we're going to have e raised to the power of y minus y and then we're going to evaluate it as bounds, and y equals 0 at the lower bound, y equals the natural logarithm of 2 at the upper bound. Oh, something interesting is going to happen here. I love when stuff like this happens. Okay, this is going to be the fundamental theorem of calculus part 2. I don't know if I'm going to have enough room. I'm going to try. So we're going to have e raised to the power of the natural logarithm of 2 minus the natural logarithm of 2. Ooh, this is a nice cancellation here. Minus e raised to the power of 0 minus 0. So what's this going to be? The exponential and the natural logarithm, they cancel each other out. And well, that's going to leave us with that's going to leave us with 2 minus the natural logarithm of 2. E raised to the power of 0 is going to go to 1. It's going to be 1 minus 0, which is 1. And so um this is going to be 2 minus the natural logarithm of 2 minus 1. And that's going to equal, we're going to combine like terms, this -1 and this 2. So that's going to be 1 minus the natural logarithm of 2. And that's going to be our answer for this one. This example says to find the volume of the solid f of x and y equaling x squared times y times cosine of x times y squared on the region where x is between 0 and pi and y is between 0 and 1. Now with this, let's draw out our region R. X is between 0 and pi. So let me see, I'm trying to like scale this properly. If 1 is like right here, then pi would be like over here-ish. So yeah, x is between 0 and pi. This is the origin. And maybe I should write that better. We know it's the origin, but and so x is between 0 and pi, y is between 0 and 1. Then the region that we're looking at is right here. That's our region R. So this is the region that I'm looking at. This is the ceiling of the function, right? This is the ceiling of the function. Then we're going to find the volume in the xy plane. This is the ceiling. And we're going to find the volume. We're going to find the shaded region underneath the ceiling, right? We're going to find what's inside. And so, well, we have to set up an integral. We have to set up an integral. We're going to do so with this formula here. This, I believe, given to us, this is the integrand. This is our integrand. And we're given the bounds of integration for each of the integrals because there's 2 of them. But there's also 2 different ways that we can orient them. There is, let's do this color. There's the first way. I could say, let's see. We'll do x first this time. The integral from 0 to pi. And then y is going to be the integral from 0 to 1. And inside of the integrand is given to us x squared times y times cosine of x times y squared. And then this is going to be dy dx. Oops, I guess technically we did the same setup last time. I don't know why I said this time. Oops. but I'm gonna leave it in there because I make mistakes. Okay, anyway, um, and then the second option that we could do is if we put y first. I guess technically we would be putting x first. We would be putting y first here. But anyway, I'm talking about the setup like with these. Anyway, it's gonna be like the integral from 0 to 1 times the integral from 0 to pi. And the integrand stays the same. It's gonna be x squared times y times cosine of x times y squared dx dy. Well, we can do one or the other. Let me just look at this for a second. One of these is significantly easier to do than the other one. Integral 2 is almost impossible to do. Maybe it is possible. Mathematics goes on forever, so technically anything's possible in mathematics. But I'm not here to talk about philosophy because let me stay focused. Um, uh, Integral 1 can be solved with U substitution. And I say that because, you know, man, I really should have practiced more of these. Ideally, I would have practiced a lot more of these because when you practice them, then you can get used to picking the right one. But I know that integral 1 is the first. I know that integral 1 is probably the first choice because you can do it with U substitution. Because if it's integration with respect to y, and I want to look at like what's on the inside of cosine of u, the trigonometric function kind of becomes a focal point in the sense that it's like if I did the inside of the trigonometric function, right, and I did I set u to be x times y squared, and then I'm going to do when I take the derivative to get my du, I'm going to take the derivative of y squared and treat x as a constant, so that gets factored out. Then I'm going to end up with 2xy. And if I end up with 2xy, it's going to be du equals 2xy, but then there's no 2, oh, excuse me, then I'm going to have du equals 2 times, yeah, 2 times x and y. But it's like, I don't have 2xy. So I can divide that du by 2xy and then start manipulating it from there. But I think that the takeaway from this problem, I like how I'm like just doing this in my head. I'm not even doing it out loud. Sorry. I'm just because I'm trying to like think about this, like what is this trying to teach us? I think that the takeaway from this is that we want to do um what's inside of if you have a product of a trigonometric function, it's probably the move to try to do U substitution with what's on the inside of the trigonometric function. So let me just get to work. Let me just get to work because we are going to do this. Um, you know, these are investigations, and I just think that's the way to go. So let's just see what happens here. It's like I got this thing, and I'm going to turn the inside integral purple because I plan to use substitution. Hey, dude, really? I plan to use substitute it. That one tried to escape. It's not funny because we're gonna be doing use substitution, and so we said that we wanted to set u equal to x y squared, and this is because it's inside of the cosine operator. And well, if that's the case, and honestly, I'm gonna do this because I'm gonna have to do those bounds of integrations. So that's the case. Du, right, is gonna be, because we're doing it with respect to dy, so it's gonna be x times d dy y squared, right, and then that's gonna be du equals 2xy. dx. Ooh, no, not even dx, dy. So that's going to be 2 times x times y dy. And we don't have, it's like we don't have a 2xy. So that's okay, because I'm going to do du divided by 2 times xy equals dy. So then that should be like that, I think. In theory. Well, the thing I love about mathematics is it's like they say everything's a theory except for mathematics. But that's just what they say, you know? Anyway, no, but I love mathematics so much. What's the upper bound? 1. So if u is x times y raised to the second, and we're doing, these are the y bounds, y, it's going to be x times 1 squared, which equals x. Wait, I should put a barrier. And then for the lower bound, it's going to be x times 0 squared, which is just going to be 0. Oh, yes. Yeah. Ooh. So let's do this. I'm drawing a barrier. The integral from 0 to 1 for the integral, which is new bounds, is from 0 to x. We just did u substitution, so it's going to be like x squared gets left alone, y gets left alone. Cosine of u is like the only thing that changes. Times dx dy. Well, dx is, oh, excuse me, times dy dx. And so dy is now du over 2xy. And then those, I could cancel a y and the x, but just one x, I think. And so dx, and so this is going to be 0 to 1. So integral, oh no, I'm going to put these back. 0 to x. This is x and x. So this is just going to be 1x. Y and y, that y is going away. It's going away. Cosine of u, but now that du just changed because we took out an x and a y, so du. Oh, but that's 1/2, I think, dx. But that's 1/2 I could factor out. I think I could factor out that 1/2, right? It's like 1/2. And I'm taking it out of both of them. It's just getting moved. It's going to be 1/2 times the definite integral from 0 to 1 times the definite integral from 0 to x times cosine of u. So this thing now, so this is going to be 1/2 times the definite integral from 0 to 1 times the definite integral from 0 to x for x. Okay, so it's going to be 1/2 times the definite integral from 0 to 1 times the definite integral from 0 to x of x times cosine of u, integration with respect to u, integration with respect to x. Now with this, we're doing an integration with respect to u, so I can just factor out that x entirely, and then I'll put it back in after we're done. So it's going to be 1/2 times, I guess it's not factored out entirely. That 1/2 isn't factored out entirely though. Because it's like a real constant. It's like a real constant. Uh, X is kind of a fake constant in this context. It's the constant context, and so this is going to be X times definite integral from 0 to X for cosine of U integration with respect to U, and then finally integration with respect to X. Now this is a little bit easier to handle. This is easier to handle because it's going to be 1/2 times the definite integral from 0 to 1 times well, for X times sine of U. Wait, derivative sine stays positive. So oh yeah, so this is going to be positive sine. So this is going to be sine of U, such that U gets evaluated at the bounds of integrations, namely the lower bound is 0 and then the upper bound is X. And well, this is going to be on the outside, it's going to be integration with respect to X. Make this nicer. This is going to be 1/2 times the integral from 0 to pi for X times sine of U integration with respect to, oh yeah, evaluated at U equals 0. I am out of room. All right, come on, let's go. I'm getting rid of this. Let's go. Come on. Here we are, guys. We've arrived at our destination. We're gonna do 1/2 times the integral from 0 to pi times X times sine of U, evaluated from U equals 0, U equals X up here, and then integration with respect to X at the end of that. We're going to take this over here, and we're going to say this is 1/2 times the definite integral from 0 to pi for X times sine of X minus X times sine of 0. Pretty sure that sine of 0 is, oh gosh, I should know this. My calculus professor would get so mad at me right now. I'm pretty sure that's 0. Where's my calculator? I'm pretty sure it's 0. I say that with actually confidence. Yeah, it is 0. Okay, so this is gonna go to 0. Means the X is gonna go to 0, so we're gonna be left over with 1/2 times the definite integral from 0 to pi for X times sine of X integration with respect to X. And with this, it's like, yeah, there's two X's. Yeah, they're, that's the variable we're dealing with, sure, but it's integration by parts. This is an integration by parts situation. And so, we got to work for it, right? This integral, it's taking us on the chase. And for integration by parts, legend has it that we will use a mnemonic device called Liate. You could think of Liate as like the SOHCAHTOA of integration by parts, if you know what I mean. If you don't, that's okay, because all Liate stands for is it gives precedence over what we're going to assign U to be. So it goes logarithms, which includes natural logarithms, inverse trigonometric functions, so inverse trig, inv trig, algebraic, which is stuff like x, like that, algebraic, and trigonometric functions comes next, and then after that it's exponents. So that's the sort of that's like the hierarchy when we want to understand what takes precedence over what as we assign U for our integration by parts. So we know it's integration by parts, and for integration by parts, I've learned of it as well. There's also another mnemonic device, and it goes ultra, violet, super, voodoo. And so all that means is that this is what the setup's going to be after I apply the integration by parts. So so we want integration by parts. And that means that we need u. That means that we need du. That means that we need v, and that means that we need dv. But honestly, the ones that we're working on actually assigning are uh, u and dv, because that's what it starts out with. Because the full formula, honestly, it goes like this. Integral of u integration with respect to v equals ultraviolet super voodoo. But you really only have to remember this part. Hence the mnemonic device. So, well, this isn't voodoo magic, it's math. And in mathematics, we have mnemonic devices like liate. That might sound silly, but come in helpful. So we look at what we're dealing with here, and we're like, all right, you know, we're just really looking at this integrand. X times sine of x. Well, logarithm? No, there's no logarithm. Inverse trigonometric function? No. Algebraic? Hey, you know what algebraic is? Actually x. So u is x. And what's the derivative of x? 1. Or just dx. And well, if we assigned, oh yeah, I probably should have not have jumped ahead. For the people who are new to integration by parts, u equals x. Okay, so then you really want to do this one next. So dv. Uh, since we already assigned x, that means that dv must be sine of x, and that is the case. So then we take the derivative of x. So the derivative of x is 1, so 1 dx, or just dx. And so we just took the derivative here, and then at this part here is where we integrate. So we anti-differentiate, if you will. And let's see. So here, if you take the integral of sine of x, it's going to be negative cosine of x. Then we throw it back into our setup. So we have all of this to put on for our formula, and this is the formula that we want to put on for. So it's going to be x times negative cosine, which is going to be negative x cosine of x, minus our other integral, which is v integration with respect to u, which is negative cosine of x dx. Oh yes, we like that. We like that a lot. Um, One thing to note is for this, we have to account for both one. So this is like the raw setup, but we have to account for this 1/2, and we also have to account for the bounds of integration. So so with that said, I'm gonna have a 1/2 on the outside because that's what we have here. And for the bounds of integration, it's like, okay, well, we have this negative x cosine hanging outside. Well, we still need that, it's still bounded. We still have to evaluate that at the bounds of integration. You can't get around that. So we already know what our bounds of integration are. It's 0 to pi, and then minus, but really there's a negative cosine, there's a minus, so it's gonna be plus. And then the bounds of integration follow suit. It's still from 0 to pi. There's no changing bounds like there is in u substitution with integration by parts. This is going to be cosine of x integration with respect to x. So with integration by parts, well, that's pretty much done right now. I'm going to have 1/2 times negative x times cosine evaluated from 0 to pi. I'm going to worry about that in a second, because to this we're going to add plus, I think it's sine of x evaluated from see right here. Evaluated from 0 to pi. Okay, so that's the same exact thing as 1/2 times this whole thing. That's going to be, well, actually, I don't even need to put another parenthesis there. This times this whole thing, which is negative x times cosine of x plus sine of x times, oh no, yeah, plus sine of x evaluated from 0 to pi. Let me just check my work really quickly. So at this point, we don't have to evaluate the lower bound because it's just going to be 0, so we're just going to be subtracting 0. But we do need to plug in pi, so it's going to be for the trigonometric functions and also this negative x here, so it's going to be 1/2 times negative pi times cosine of pi plus sine of pi, right? And well, sine of pi is the x coordinate on the unit circle, which is 0 at pi. Cosine of pi is -1. -1. So it's going to be 1/2 times negative pi times -1. And that's going to be 1/2 times pi, which is the same thing as pi halves or 1/2 pi. And that's going to be our answer. Let's begin our discussion on the average z-value of a function. Over a plane region, R is denoted by f bar, and f bar equals 1 divided by the area of the region times the double integral of f of x and y. So, you know, we look at this and we're like, okay, but what is volume? Like, what is a volume? What is a volume? All this time we were talking about volumes, but like, what is a volume? Well, if you think about it, you have an area times a height. So if I have like a rectangular solid here, and I have my area times my height, well, the double integral of f gives you the volume, right? If I have a double integral, the double integral of f, that gives me my volume. And yeah, so if I take the volume, and I divide it out by the area, I get the height, right? So if I have my volume and I divide it by the area, then I get the height. But this height, it turns out to be the average height the whole time. So if you want to find the average height or the average z-value, it's 1 over the height times the double integral. And the double integral is the volume you're dividing out the area, which is what we see here. So let's work through an example. This example, it says find the average value of f of x and y when it equals 2 minus x minus y over r. And r tells us that x is going to be in between 0 and 1, and y is going to be in between 0 and 2. And so this here is the function. So the region, this is in the xy plane. X goes from 0 to 1 and y goes from 0 to 2. So we know how to draw this out. So let's see here. We got our x, we have our y. This can be 1 here, and this can be 1, and this can be 2. And well, if x goes, let's see, if x goes from 0 to 1, that's from here to here. And if y goes from 0 to 2, that's from here to here. So I know that the region in question that we're looking at is right here. and this is my region. So this is the description of the surface above it, the z value, so to speak, the ceiling. In a situation like this, we could try to like visualize what the integral is going to look like in our head. We could do, I mean, honestly, we could write it out. Let's not try to do any trick shots. We're going to do first integrals is 0 to 1. That'll be the x. This will be with respect to y, so this will be from 0 to 2. Our function is right here. 2 minus x minus y dy dx, or we can do definite integral from 0 to 2 times definite integral from 0 to 1 of 2 minus x minus y dx dy. And so both of these are going to be the same level of difficulty. From looking at this, it's like it's just the same level of difficulty. It's like there's there's an x, and there's a y. There's a constant, there's an x, there's a y. And the x and the y, they're going to be treated as constants regardless, depending on which way you go. Of course, it will depend which one at which time, but it's the same level of difficulty. And so the area of R, we can calculate what the area of R is, because the area, I guess I didn't write it out. The area is length times height is area. So like we can calculate the area of this thing because we know that area equals length times width, or if you'd like, area equals length times height. If we say that this is the height and that this is the length, then well, and whatever you want to name it, it's going to be 2 times 1, and 2 times 1 is 2. And so that's our area. The area of R is 2. From our formula, we can utilize this here. We can utilize our formula here. Can we? Yeah, we can. So this is the formula that we want to use. We want to use our F bar formula. We just calculated the area of R. So if we want F bar, we can go, we can say that like F bar equals 1 over 2. And that's times the double integral, which is, let's do this one, shall we? So 1/2 times the integral from 0 to 2 times the integral from 0 to 1 of 2 minus x minus y dx dy. And so in this case, well, we're integrating with ooh, wait, that's a really pretty blue. Hold on. Yeah, okay. Well, in this case, this y here, this y gets treated as a constant. We can even, but before that, let me just specify that this is a linearity rule. But y still gets treated as a constant either way. And well, since that's the case, what we're going to end up having is we're going to have 1/2 times the definite integral from 0 to 2 for, well, 2, the integral of 2 is just going to turn into 2x. Well, I have 2x minus, well, the integral of x with respect to x is going to be a power rule. So it's going to be 2x squared over 2 minus, well, y gets treated as a constant, so we're just going to put an x onto that y. So what's going to end up happening is it's going to be a situation where it's going to be 1/2 times the integral from 0 to 2 of 2 times x minus x squared over 2 minus x times y, evaluated from 0 to 1, I'm pretty sure. I just realized something. Because this is a double integral, I should specify that this is x equals 1 and x equals 0. And so and so I'll evaluate this at its bounds, but not really, because I'm going to skip doing x equals 0, because we know that we're just going to end up with minus 0. The only time that's arguably like, I mean, I don't know. Maybe I won't. Maybe I will do it. Okay, I'll do it. You've convinced me. But the only time where I would say is super, super important to always evaluate the bounds of 0 is if you have like a cosine of x and you're gonna fill in x, but we don't have that in this case. And so what are we gonna have? 1/2 times the integral from 0 to 2. Let's see. 2 times 1 minus 1 raised to the second power over 2 minus 1 times y. And from this, we'll subtract our lower bound. Oh, well, the function evaluated at the lower bound, that is 2 times 0 minus 0 over 2 minus 0 times y. And this is all within an integrand. That is the integrand for 1/2 times the definite integral from 0 to 2 integration with respect to y. And so, well, this is just going to go to 0. The second term is just going right to 0. As for the third term, as for the first term, there is no third term. Actually, technically there is, because I could say this plus 0. But for the first term, I'm gonna say that this equals 1/2 times 0, or excuse me, times the definite integral from 0 to 2. This for the first term, it's gonna be the new integrand, so it's gonna be 2 minus 1/2 minus y. Integration with respect to y. And well, we know how to do this. This is just gonna be a linearity rule. I'm trying to think if I should just, yeah. And so this is gonna give me 1/2 times 2y. Excuse me. This is gonna give me 1/2 times 2y minus 1/2 y minus y raised to the second power over 2. And this is going to be evaluated from 0 to 2. And so, well, if that's the case, then I could say that this is going to be 1/2 times 2 times 2 minus 1/2 times 2 minus 2 raised to the second over 2. And this should be parenthetical. Minus the lower bound, so 2 times 0 minus 1/2 times 0 minus 0 raised to the second over 2. And, well, this whole thing is going to go to 0. But as for this thing, it's going to be a situation where it's like 1/2 times 4 minus 1 minus 2, right? Because, yeah, I think. And then, well, this is just going to equal 1/2 because 4 minus 1 is 3, minus 2 is 1, and then 1 times 1/2 is 1/2. And so the answer will be 1/2. In this next part, we'll talk about finding the volumes of surfaces over regions that aren't rectangular. This is double integrals over general regions. So we'll open with an example. Let the region in question R uh, show that x is in between -1 and 2, and y is in between 0 and 5. So x is from -1 to 2, and well, y it's from 0 to 5. 1, 2, 3, 4, 5. And so, well, as it turns out, our region in question should look something like this. Okay? This is the same exact region. This is the same exact region here. I just want to show that on a rectangular region, the rectangles are the same length for all x's and for all y's. Because if I look at this and I start drawing rectangles inside of this, right? For um for all x's, all of these rectangles, all of these vertical slices are going to be the same. And for all y's, all of the vertical slices are going to be the same as well. dy, would be dy because dy is the horizontal slices, and when the vertical slices here, this is going to be dx, right? Integration with respect to x. That's the vertical slices. So in a rectangular region, the rectangles are all the same length for x's and y's. So for this, it's like, and maybe I'll write that down. Let's write down our rule. So what this means, as a result of this rule that we've established, is the setup could go either way, right? I could write this thing as the definite integral from 0 to 5 times the definite integral from what is it, -1 to 2, and then the function is some function f of x and y, dx dy, or I could rearrange this thing. And then I'm just gonna switch this around a bit. Okay, no, and it could look like this. It does not matter. One thing to note here is that this one, the integral from 0 to 5 times the integral from -1 to 2, for some function, integration with respect to x, integration with respect to y, it has dx first, so the bounds are left and right, and it also has dy second, and it has dy second, so the bounds are down and up. All right, so that's the deal with that. So that's the mechanics behind this thing. Let's look at another example. In this next example, we're given a graph. It says to let the region R be this graph. And this graph, we're given a cubic, x raised to the third power, and we're given a linear function that is 4 times x in blue and x raised to the third in red. And we're told to build this double integral f of x and y, integration with respect to y and integration with respect to x. And it's like, well, the thing with this is that dy is first. And since dy is first, it's the inner. It's the inner integral, so we evaluate that first. We need to bound the top and the bottom. We need functions of x as inner bounds, so we're going to solve so we can solve the equation for y. So basically, um, you know, let's say I'm going to move this over here. So dy it's first, right? Dy is first, and it's the first because it's the inner. It's on the inside here. Okay, so dy is first, and and so what that means is that we need to bound the top and the bottom. That's right here. We need to bound the top and the bottom because those are the vertical slices. So let me write that out. And what's more is that we need functions of x as inner bounds so we could solve the equation for y. Perhaps I should have done this sooner, but in here, this is the region that we want. All right, this is region R. And so it's like we said over here, right? We need to bound the top and the bottom. So we can bound the top. We need to bound the top and the bottom. So we can bound the top and the bottom like that here. Take a vertical slice. And so well, we can see that the top of the rectangle, it's 4x. And the bottom of the rectangle, which is this red line here, that's x raised to the third. For dy, which comes first, this is going to be the inside. It's going to be x raised to the third power on the bottom, because we could see that. And then on the top, we could see that it's going to be 4x. That's the top of our rectangle there. And then on the inside, we'll have our function, f of x and y, and that's dy, right? So that's our vertical slice. We need functions of x as inner bounds to solve the equation for y. And so to do this, we have to set these equations equal to each other. So say 4x equals x to the third power. Then with that, I'm going to say that I'm going to move that 4x over. I'm going to say, well, then x3 minus 4x equals 0. Okay. Then from this, I'm going to say I'll factor out an x from both of these. So then I'll have x times x squared minus 4 equals 0. And then I think that's a difference of squares situation. So it's like, okay, then if that's true, then x times x minus 2 times x plus 2 equals 0. Then there are 3 different answers that we get from this. The first one is x equals 0. The second one is x equals 2. And the third one is x equals negative 2. But since we're in the first quadrant here, we know that this x equals negative 2, that can't be the case. So it has to be these two. So what I'm trying to say is that the outside integral, the integral with integration with respect to x, is going to be the integral from 0 to 2. And then we'll put an integration with respect to x on the outside of that. And so what we just did is we reduced dx one dimension just to find the bounds on x. And so this would be the setup for the first integral. Okay. For the second integral, it's a little bit different. So that's going to be the setup for the first integral. But we can also build the other one, right? So like say that we're supposed to build now we're told like build the double integral for f of x, y, dx, dy. What is that asking of us? If it's asking us to build this, that's going to be our horizontal slice, right? We're doing rectangles here. And in this case, dx is first. Dx is the inner integral. So since that's the case, we need to bound this thing. We need to bound the left and the right. And we also need functions of y as inner bounds so we can solve the equation for x. I'm gonna utilize the space up here. So let's look at the left bound. And honestly, look, I'll draw a border. I really want to do this all on one page. So first we'll look at the left bound. It's the lower bound. Right, that's the lower part of the rectangle, the left bound. At the left bound, the lower bound, that's this blue line, y equals 4x. Y equals 4x. Or another way that we could think about this is y over 4 equals x, right? And then for the right bound, that's the upper bound. It says that, well, since it's a cubic, y equals x raised to the third power. Or what is this going to be? The cubed root of y equals x. So then, so now we have like the inside. So we have the inside, we have the inside integral. We have the inside integral now. That's so the lower bound is, because we're doing x, so the lower bound is y over 4. And then the upper bound, it's the right bound right here, is gonna be the cubed root of y. Okay, and that's for our function f of x and y, and we're doing dx first. So this one, so now we have to reduce it to one dimension and find the bounds on y. We want to see where it's intersecting. Dude, can I just Desmos this? Oh, Desmos y equals x raised to the third, and that is the second. Y equals x raised to the third, and what is it? Y equals, is it 4x? So I'm going to use my graphing calculator. Hey, look. They intersect at 2, 8. And they also intersect here. So these are the two intersection points. They intersect at 0, 0, the origin, and they intersect at 2, 8. I'm going to write down that they intersect at x equals 0 and x equals 2. And at x equals 0, at x equals 0, where are we? If x is 0, then y equals 0 raised to the third. Or at x equals 0, y equals 4 times 0. And 4 times 0, or y just equals 0. what was the other intersection point? X equals 2. So then at x equals 2, at x equals 2, what happens? We get y equals 2 raised to the third, or y equals 2 raised to the third. 2 times 2 is 4 times 2 is 8. Or in the other case, y equals 4x, plug in x for 2, or plug in 2 for x, equals 4 times 2, which in that case also equals 8. So we can confirm that y equals 8. So, so we have y equals 0 and y equals 8. We just plugged in the two x intersection points, right? So so this integral on the outside here is going to be from 0 to 8, and then integration with respect to y. And so this would be the setup to build the other one. And that's how you would do that. Oh, it's 4 a.m. I know that time. It means it's time for another one. This one says to evaluate the integral from 0 to the natural logarithm of 2 times the integral from e raised to the power of y to 2 for y over x, integration with respect to x, integration with respect to y. Well, for this one, I'm going to manipulate this a bit. So I'm going to have integral from 0 to the natural logarithm of 2 times Euler's number raised to the power of y times the integral of Euler's number raised to the power of y, times the integral of from Euler's number raised to the power of y up to 2. So I'm just going to manipulate the integrand. I'm going to say I want to move that y over. I'm going to have y times 1 over x, integration with respect to x, integration with respect to y, which ultimately is going to have me just sort of disregarding that y for now, because it's like, well, I'm going to factor it out entirely because I can treat it as a constant due to the fact that we're doing integration with respect to x first. So I'm going to have inside of the integral 1 over x, integration with respect to x, integration with respect to y. And then the key here is, well, it's the fact that we know from our formulas that the integral of 1 over x, integration with respect to x, equals the natural logarithm of the absolute value of x. Absolute value of x. Or if you like, the natural logarithm of x plus c. So that's the formula that we'll be applying to this here momentarily. And well, once we apply that, it's going to be the integral from 0 to the natural logarithm of 2 for y times the natural logarithm of x. Of course, there won't be a plus c because we do have an evaluation bar. We do have our bounds of integration. That is namely the lower bound e raised to the power of y and 2. And then we'll have a dy in the end. Oh yeah, and I should specify that this is going to be the limits of integration that are set to x. So x equals e raised to the power of y. For the lower limit of integration, for the upper bound of integration, x equals 2, and with respect to x. So now at this point, I'm going to evaluate these things at the bounds. I'm going to evaluate these things at the bounds. So I'm going to have the integral of from 0 to the natural logarithm of 2 times, well, I could do it like this. y times the natural logarithm of 2, that's the upper limit of integration, minus y times the natural logarithm of Euler's number raised to the power of y. And well, upon doing that, we're going to have these inverse operators interacting with each other where they cancel. And it's going to turn into the integral from the natural logarithm of 2 for y times the natural logarithm of 2 minus y times y. Integration with respect to y. This is going to turn into y squared. So if this turns into y squared, it's going to be like 0, the integral from 0 to natural logarithm of 2, and it's going to be y times the natural logarithm of 2 minus y squared. And then that's going to be natural logarithm of 0 to the natural logarithm of 2 for, in the integrand, it's going to be y times natural logarithm of 2 minus y squared, I believe, dy. So for this one, the natural logarithm of 2 is a constant. So it's going to be like, it's kind of weird, but it's going to be like the integral from 0 to the natural logarithm of 2. And I'm going to split this up via the linearity rule just because that's how I roll with this kind of stuff when I just don't want to make mistakes. So it's going to be y times the natural logarithm of 2 dy minus the integral from 0 to the natural logarithm of 2 for y squared dy. And then at that, I'm going to factor out that natural logarithm of 2, multiply that to the integral from 0 to the natural logarithm of 2 for y dy minus the integral from 0 to the natural logarithm of 2 for y squared dy. Then we can get to evaluating this because it'll be easier to see, hopefully, that this is going to be y squared over 2 times the natural logarithm of 2 minus y cubed over 3 evaluated at y equals 0 and y equals, for the lower limit, and then for the upper limit, y equals the natural logarithm of 2. And gosh, well, we're just gonna plug in for y. Well, that's gonna be natural logarithm of 2 squared over 2 times the natural logarithm of 2 minus the natural logarithm of 2 cubed over 3. From this, we're going to subtract a 0 because that's the lower limit of it. Wait a second. Are we sure about that? Yeah, we're sure. So then from this, we're just going to subtract a 0. Now at this point, I'm going to do some factoring. I'm going to say that this is 1/2 times the natural logarithm of 2 cubed, right? Minus 1/3 times the natural logarithm of 2 cubed. Of 2 cubed. And then what? Then it's like, can we factor out a natural logarithm of 2 cubed for both of these? You know, and then see how those fractions interact with each other. Because if I'm like, okay, well, I'm going to take out the natural logarithm of 2 cubed and then multiply that to 1 over 2 minus 1/3. This is going to be a lot easier to get these to interact with each other, I think, because the natural logarithm of 2 raised to the power of 3 times what's the common denominator between these guys is going to be like 3 and 6 minus 2 and 6, right? That equals the natural logarithm of 2 cubed times 1/6, I think. Then it's like I can combine these and say that I'm going to put this over 6, right? Like I'm going to have the natural logarithm of 2 raised to the power of 3 over 6. And then that's going to be my answer for this. So that's how you would do that. Behold, it is time for another problem. For we are to rewrite the integral, the definite integral from 0 to 3 times the definite integral from 0 to 6 minus 2 times x for the function f of x and y, integration with respect to y, integration with respect to x, as the double integral of f of x and y, integration with respect to x and integration with respect to y. So basically, it's just, it wants me to flip the bounds of integration. And so, well, to do this, the first thing to do is to sketch the region. We're going to sketch the region R. So we're going to sketch the region. That's the first thing to do. And from the bounds, well, the dy bounds of integration, that's what bounds y. And the dy bounds of integration is saying that y is between 0 and 6 minus 2x. And for x, it's saying that x is between 0 and 3. So let's just write that out. So the dy bounds of integration, that's what bounds y. And we know that y is in between 0 and 6 minus 2x. Okay. So then dx bounds of integration. Well, the dx bounds of integration, that's what bounds x. And it looks like x is in between 0 and 3. So what we're going to have to do is we're going to have to try to draw this out. Let's draw a cool R. Look how cool that R is. Anyway, so let's just try to draw this out. Honestly, I'm going to draw it out over here. I'm going to try to draw it out over here. I don't know. Let me just see something on my calculator really quickly. I'm going to graph the upper bound of integration for y. Because I think that's the curve that it's under. Yeah. Okay, so we're gonna graph our region. We're gonna try to. And well, we have to like we have to graph the upper bound for y because we know like that the we know that x goes from 1 2 3. Well, maybe I should try to do this better. So this is going to be like because we know that x goes from 0 to 3. So, that's 1 2 3. And then then what's the region that bounds x? So we're gonna graph this curve here. 6 minus, because this is y. So 6 minus 2 times x. The x-intercept, excuse me, the y-intercept is 6. So 1, 2, 3, 4, 5, 6, right? Something like that. And then let's try to graph this thing. Right? So and then it's gonna intersect. So if I drop a, well, it's actually gonna drop it diagonal. So the line is gonna intersect the line is gonna intersect the y-axis at um at 6, and then it's gonna cross over it's gonna cross the x-axis at 3. So um so this is the curve or the line that we're working with. Pretend that's linear. I know that doesn't look good. Hold on. Whatever, something like that, right? And this is y equals 6 minus 2x. Um, so, so what, so we want to have dx first. We're told that we want to have dx first. And dx first, that means it's going to be the inner. So the bounds are left and right, and the bounds of function y solve for x. So we want dx first, which means that it's going to be the inner. And the bounds are from left to right. And then the bounds function of y solve for x. These are going to be horizontal slices, aren't they? Horizontal, something like that, I think. And so, well, at the left side, and I'll write this over here, but the left is the lower bound, and well, that's going to be at x equals 0. The right, it's the upper bound, and the right is the upper bound, and that caps at y equals 6 minus 2x. So that caps at y equals 6 minus 2x. Or if we wanted to solve this thing for x, I'm going to say plus 2x on both sides. That's 2x plus y equals 6. Move that y over, and that's going to be 2x equals 6 minus y. Divide both sides by 2. That's going to be x equals 6 minus y over 2. And then that's also the same thing as x equals what? 6 over 2 minus 1/2 y, which is the same thing as 3 minus 1/2 y, I think. Okay, so so uh so then what that means, I think, is that I think that's right. And so I think that the setup for this now is, well, we know that um we know that y is from uh we know that y is from 0 to 6. So it's going to be like the integral from 0 to 6, right? And then we have our new x, right? So we know that x is 0 here. But then here it's 3 minus 1/2 y for the upper bound. 3 minus 1/2 y. And then inside of our integral, we'll just put our arbitrary function there. And then with the dx dy business as well, we've changed it. So we've effectively changed it. So it is dx dy now. And so this would be our answer. That is the integral from 0 to 6 times the integral from 0 to 3 minus 1/2 times y for our arbitrary function f of x and y, integration with respect to x, integration with respect to y. And so that would be the answer for that. 2, 4, 6, 8. Time to learn to integrate. This one says to change the order of integration for the integral from 0 to pi times the integral from x to pi for sine of y squared, integration with respect to y, and integration with respect to x. So this integral as is cannot be evaluated. So the trick is to reverse the order of integration and make this something that we can actually evaluate. Now, I want to make it dx dy. I want to flip them around. So the first thing that I need, so the first thing that I need is I need the region R. So first I have to find the region R. Now dy is first, so x is the lower bound, and pi is the upper bound, and dx is is second, and so it goes from 0 to pi. So this tells me two things. The first thing that this tells me is that x is to be less than or equal to y, and y is to be less than or equal to pi, right? So y is in between x and pi. And it also tells me that 0 is to be less than or equal to x, and x is to be less than or equal to pi. In other words, x is between 0 and pi. So y is bounded by y is bounded by y equals x on the bottom and by y equals pi on the top. So I'm going to try to draw this. I want to turn our attention to this here. X is less than or equal to y. So this here is important because this means that x could be equal to y, but it could also be less than y. So that creates a border. If we graph the line x equals y, then it's going to look like this, a straight line, right? Straight line, but this line is y equals x. As for this here, well, this here says that y is less than or equal to pi. Y is less than or equal to pi. So let's see. So if y could be equal to pi, we could graph y equals pi. So let's see. 1, 2, 3.141592655359. And so that could be right here. I'm trying to say this is y equals pi. So that means that so that it's bounded. It's bounded in this region here. The bottom bound is the red line, and that's y equals x. And so so let's look at the bounds of this thing. You know, like what are those? You know, there's my horizontal sliver, my slice. We look at this and we're like, well, what's the lower bound? So the lower bound is 0. Well, what's the upper bound? Well, the upper bound is x equals y, this red line. That's the upper bound. And so we'll write that out. The lower bound is x equals 0. That's our y-axis. And the upper bound is y equals x. And we also know that y is somewhere between 0 and pi. What are we even doing? I want to flip it. We need to flip it. I want dx to come first. And since I want dx to come first, that means that I need to solve all of these things for x. So if I want dx to come first, I try to bound this from the left to the right. And the left bound is always going to be x equals 0, and the right bound is always going to be x equals pi. Excuse me, y equals x. Sorry, I was looking at this. Um, so right, the left bound is always going to be x equals 0. The right bound is always going to be y equals x. Like I know that this is pi, right? We said it's pi, so this y equals pi, it's pi. Um, and well, x equals pi is where these things intersect. They intersect at when x equals pi. And if y equals x, then that means that y has to be pi as well. The intersection point is at x equals pi. So if they intersect right here, I can drop down and I could say that this right here is pi. And if y equals x, or x equals y, then y has to be pi as well. So the lower bound is x equals 0, and the upper bound is y equals x. And so we know that y is in between 0 and pi, right? But then it's like, if I want dx to come first, I'm trying to bound this from the left to the right. The left bound is always x equals 0, and the right bound is always y equals x. The big bound is y. Since I solved, say I solve it for x, and the lower bound is 0. And if this goes from 0 to y, to get the dy, I just have to figure out what number is on the y-axis, which is pi, and what number is on the y-axis, and what numbers are used on the y-axis, what's bounding it, and x equals pi is where they intercept, and if y equals x, then y has to be pi as well. So you'll notice that y goes in between 0 and pi, right? So if that's the case, then I'm putting y to the outside, so it goes in between 0 and pi. Okay? Well, this is my y-axis, this is my x-axis. Should have labeled them. So that's why I'll get 0 to pi. As for the x-axis, well, the lower bound is 0, and the upper bound is y. So this is going to be the integral from 0 to pi times the integral from 0 to y for sine of y squared, integration with respect to x, integration with respect to y. And this is now a solvable integral. This is now a solvable integral, and this is called an iterative This is called an iterative integral. This can be solved with u substitution. So if we want to look at this, right? So I want to do this inside integral first. So to evaluate the blue integral, we notice that its integrand, it's integrated with respect to x, which means that we are going to treat sine of y squared as a constant in its entirety. So we're just gonna factor it out of the integrand. And a 1 on the inside, if I want to integrate 1, it's just going to be x. So this is going to be x evaluated from, I should be specific, x evaluated from x equals the lower limit, which is 0, and evaluated at the upper limit, which is y, dy. And so now it's going to be integral from 0 to pi Now this is going to be the integral from 0 to pi for y times sine of y squared dy. And oh, what is this? This is so we can solve this with u substitution, I think, because yeah. So yeah, this integral can be solved with u substitution. So let's do u sub. Oh, that u sub. Oh yes. How we love our u sub. We do. U substitution is that for real. It's got it going on. And so this is gonna be u equals, I presume this is gonna be y squared, right? Y squared du, what's that? What's the derivative of this? 2y. Oh no, we don't see a 2y, but we do see a y. Oh yeah, this is gonna be dy. Sorry. And so then we could do 1/2 du, right? 1/2 du equals y dy. And oh yeah, we have that. But what about our upper and lower limits? Oops. What about our upper and lower limits of integration, huh? Well, that's a good question. I don't even know what's going on with that. The upper limit is going to be pi squared. And then the lower limit is going to be 0 squared, which is just 0. Oh, okay. So let's solve this. Let's solve this. The integral from 0 to pi squared, and then in the integrand it's going to be sine of u times 1/2 du. And then this is going to be 1/2 times the integral from 0 to sine square to pi squared for sine of u du, but then this is going to turn into 1/2 times negative cosine of u such that u's upper limit of integration is pi squared. And the lower limit of integration is going to be 0. And so we're going to leave the 0 alone for now. Well, we're not going to evaluate it at 0. Wait a second, maybe we should evaluate it at 0. I think we do have to actually evaluate it at 0 because cosine of 0, what's cosine is the x. So cosine of 0 is actually 1, but it's -1. Oh, so we do have to evaluate it at 0. So it's going to be -1. So this is going to be 1/2 times negative cosine of pi squared plus 1 because cosine of 0 is 1, but there's a negative out in front of it. So it's going to be plus 1. But then this is the same thing as 1/2 times 1 minus cosine of pi squared. So this is the same thing as 1/2 times 1 minus cosine of pi squared. And so that's our answer to this problem. We indeed want to do another problem. This one says to reverse order of integration for the integral from 0 to 2 times the integral from 0 to 4 minus x squared for x times Euler's number raised to the power of 2 times y over 4 minus y integration with respect to y integration with respect to x? Well, the first thing that we want to do is we want to find region. We want to find the region. So we want to find the region. Oh, so let's see, finding R. Let's find R. Let's find our region. Well, the thing is about this is it's like where this is given away to us. Like so dy, right? These are the so this is what so this is y. This gives away what y is between. Y is less than no, 0 is less than or equal to y, and y is less than or equal to 4 minus x squared. That just means that y is in between 0 and 4 minus x squared. And what's more is this integral on the outside gives us what x is in between. Oops. This integral on the outside gives us what x is in between. So x is going to be between 0 and 2. So one thing that I want to point out here is that, well, we see that 0 is less than or equal to y. And then here I want to point out that um, y is less than or equal to 4 minus x squared. So y is less than or equal to 4 minus x squared. And so what we'll do now is we'll try to draw out the region. This is my y-intercept. So I know that I'm scaling this for 1, 2, 3, 4, where the line intercepts, where the line where the y-intercept is 4. And then for how I'm going to scale the x-axis is like, well, I know x is in between 0 and 2. So 1, 2. Try to spread it out. 1, 2. And so I'm going to graph this line here, 4 minus x squared. And I know it's going to drop down like this, and it's going to intercept the y-axis at 4, and it's going to intercept the y-axis, excuse me, it's going to intercept the y-axis at 4, and it's going to intercept the x-axis at 2, right? And so now it's like, I know that this here is my region in question. This red line here is the line y equals 4 minus x squared. All right, now it's like I want to put dx first. So I need to solve all of this stuff for x and look from left to right. So left to right is going to be, I'm going to make my rectangle like this. Well, maybe I'll put it above the r. So that's going to be my rectangle. All right. So I'm going to put in all of my rectangles here, and I'm going to put them all in from left to right. And the lower bound for all of these rectangles that I'll be putting in here, the lower bound is going to be x equals 0. All right, so the lower bound is x equals 0. Now the upper bound is the red line, right? The upper bound for all these rectangles is the red line, and well, I'll have to solve that. So let me be very specific here. Of course, we need to solve this thing for x. We need to solve y equals 4 minus x squared for x, so we can insert that as our upper bound when we do integration with respect to x. So so let's just do that. Let me underline this. Let's just do that. Y equals 4 minus x squared. I want this with respect to x, so I'm gonna add x squared to both sides. This is going to be y plus x squared equals 4. I want that y to go away to the other side now. So this is going to become x squared equals 4 minus y. I need to isolate my variable, so we'll take the square root. X equals the square root of 4 minus y. What do you mean? Why are you doing why didn't you put plus or minus? Because it says right here that x is greater than or equal to 0. So it's greater than or equal to 0. It's not minus the negative square root of 4 minus y. So it is indeed plus the square root of 4 minus y. So so we'll do this like this. The x, or excuse me, the dy goes from 0 to 4, right? dy goes from 0 to 4. But next up, we have this. All the lower bound is x equals 0, which we can see right here on our rectangle. So the lower bound is 0. The upper bound, well, the upper bound, when after we solve it for x, we see that x is equal to the square root of 4 minus y. And so that makes the upper bound for the square root of 4 minus y, the positive square root of 4 minus y. The integrand stays the same. This is going to be x times Euler's number raised to the power of 2y all over 4 minus y. And then and so we just flip the integrals around. So this is now going to be dx dy. And so this is our answer here. This is what the integral would look like if you wrote it in terms of reverse integration. I tried to recreate this in red, but I hate it. So we're going with my notebook version. Here is my notebook version of this. So this question says to find the volume of the solid bounded by the cylinder z equals 2 minus y squared, the xy plane, the xz plane, the plane y equals x, and x equals 1. So this is a slice. This is a slice of a cylinder. And it's bounded by the xy plane, which is what we see down here, and the xz plane, which is from here to here. And it's also bounded by the plane y equals x and x equals 1, which we can see right here. And so with this, we need to use a formula. All right, so it's our formula. It's the double integral formula that we've been using. And well, we're given this. It says, find the volume of the solid bounded by the cylinder, and this is the cylinder here. And we know that z, it's just another name for f of x and y here. And so that's also if that's the case, then we know z is equal to 2 minus y squared, and then this is the ceiling. Oops, I don't know how to spell. This is the ceiling. And so let's try to draw this region. Let's try to draw this region in the xy plane. R in the xy plane. The region in question. The region of the hour. I can't imagine this problem. This problem is not gonna take an hour. So yeah. Okay. So we're looking at this thing in the xy plane specifically. So we can see that this thing comes out of the origin right here at like a diagonal way, and that's going to be y equals x. So y equals x is coming out of the origin here, and it's coming out like this, right? And this comes out at a right angle from the x-axis, and that would make sense because that's x equals 1. When you have x equals 1, that's going to shoot out of the x-axis there. So to be very specific, this first line here is y equals x, and that's what we see right here. And then the second line is going to be x equals 1, and that's what we see right here. Okay? So now we label our axes, because I just made a rookie mistake by not labeling them. And so this is the region in question inside of this triangle thing. Here's an angle, but we are interested in this, what's going on inside of this region here. This is our region R. We want to build dy dx. So we'll build dy first. Let's build dy first, and that's going to be our inner. It's going to be the inner integral. So we're going to do dy first, which means we're doing vertical slices. And so if we're doing vertical slices, it's going to look like this. That's dy. And so dy, we need to look at like what's the top and the bottom. What's the top and the bottom function of x? You know, like what is that? The top function of x, it's gonna be right here. The top is y equals x, and the bottom, it's 0. It's 0. So that's y equals 0. And x is between 0 and 1, right? We can see that because x equals 1 here, right? And 0, 0 is right here. So we can say also that x is between 0 and 1. And so if that's the case, then it's like we can set up our integral. So v equals, well, x is in between 0 and 1, which we can see quite clearly. So that will be x. As for y equals x and y equals 0. So the lower bound is going to be 0, and then the upper bound is going to be x. And then our function, it's the same. It's the ceiling, that's 2 minus y squared. Dy, because this is for dy here, this is for dy. And then dx, because this is our x. And so we can go ahead with this. So I'm going to do integral from 0 to 1 times integral from 0 to x for 2 dy minus integral, and I should put this in brackets, times minus integral 0 to x for y squared dy, and then dx on the outside, and that's just a linearity rule. And then it's like, well, then this is going to be 0 to 1, integral from 0 to 1 to x, so, or yeah, that's going to become 2y, I mean. So we're going to have 2y minus power rule, y cubed over 3, evaluated from 0 to x. So it's going to be integral from 0 to 1 of 2y minus y cubed over 3. And then the bounds, these are the y bounds. So this is going to be 0 equals y and x equals y integration with respect to x. And then this is going to equal what? This is going to equal the integral from 0 to 1 of 2x minus x cubed over 3, integration with respect to x. Now it's a linearity rule. So it's 2 times integral from 0 to 1 of x integration with respect to x minus another factorization here. 1/3 gets taken out, or constant multiple rule, whatever you'd like, times the integral from 0 to 1 times, no, 4x raised to the third integration with respect to x. Now this is going to be 2 times x raised to the second over 2, and I'm just going to put this in brackets because I am going to be putting an evaluation by the end. X2 over, or x raised to the second over 2 minus 1 over 3 times a quartic here, x to the fourth over 4. And this whole thing gets evaluated from 0 to 1. Well, if that's the case, it's going to be like 1 minus 1/3 times 1/4. So what is this? 1/12. 1 minus 1/12 equals, well, 12 minus 1 is 11. So this is going to be 11/12. And that's going to be the answer. So this example says to find the area of the region bounded by y equals x squared, y equals 5 times x plus 6, and y equals 6 minus x in the first quadrant. Now, in a problem like this, the first step would be to sketch the region. So I'm going to sketch out the region. We can sketch the first line. Let's let the first line be this red color, y equals x squared. And so this is exponential growth. This is y equals x raised to the second power. 5x plus 6, that can be this blue color. That's going to come shooting out of the y-axis at y equals 6. It's going to be y equals 5x plus 6. This green color, this can be 6 minus x, y equals 6 minus x. That's going to cross over at this is going to cross over the y-axis at y equals 6 minus x. And so well, here we'll use dy dx because it's easier. And the reason is because dy means that you solve the function for y. So you can get x's to put in the bounds. And they generally come solve for y. So I'll try that first. See, if I did dy first, that means that I need to bound my up and down. That means that I need to bound my up and down for the y values. And you'll notice that, well, at right here, let me see. Maybe I'll introduce some more color. I have, so there are some intersection points, right? So like this, here's an intersection point right here. And here's an intersection point right here. And so, well, I can call this intersection point P, right? And then this here, I can call this, which is, so like if this comes down, that's my intersection point, and that is right here. And this could be the intersection point Q. And so you'll notice that at point P, right here, to the left of point P, the bottom is the green line, and then the top line is blue, but then it changes because to the right of point P, the bottom is the red line, the top is blue. So I need to figure out where P is and where Q is because that's where the region stops. So I can figure out how to break this up, because I'm gonna need 2 integrals to do this. So I need to figure out where P is, and I need to figure out where Q is because that's where the region stops. So I can try to figure out how to break this up. And it seems I'm going to need 2 integrals to do it. So to find the integral on the left, the top is 5 times x plus 6, and the bottom is is 6 minus x. On the other side, the top is 5 times x plus 6, and then the bottom is this x squared. So I'm going to figure out what points p and q are so I can break this into two integrals. And I will be doing dy dx, and the reason for that is oh yeah, I already said the reason for that. Right? So we've established we're doing dy dx because that's the up and down, that's up down rectangles. This is one of the intersection points. The bottom is green and then the top is blue. So I have this one slice here. This shows that the bottom bound is 6 minus x and the top bound is 5x plus 6, right? But to the right of this p, to the right, and we draw a slice, well then the bottom is the red line. The bottom is x squared and then the top is 5x plus 6. So it switches, right? So I need to figure out where p is and where q is, because that's where the region stops. So if I can figure out what those are, then I can set up my integrals, and I'm going to need two integrals, right? So to find the integral on the left side, the top is 5x plus 6, and the bottom is 6 minus x. And on the other side, the top is 5x plus 6, and the bottom is x squared. And I'm going to figure out what points p and q are, my intersection points, right? The x point, at least, at which they intersect, because I'm going to be breaking this into two integrals. To figure out p, it's where the green one and the red one bump into each other. So to find p, where y equals 6 minus x intersects y equals x squared, to do this, to find the intersection points, all we have to do is set them equal to one another. These 2 points, the lines that we're talking about, the components that make up this intersection point, 6 minus x, and I'm going to set that equal to the other one, which is x squared. So if I set that equal to x squared, then I need to solve this. I need to solve this thing. So I'm going to put everything onto one side. I think I'll put everything onto one side. And so that's going to be 0 equals x squared plus x minus 6. And so one thing we might want to think about is that, well, this looks awfully like our our typical standard quadratic. We know how to solve a quadratic equation, right? We have to factor this. Okay. So this looks awfully like a quadratic. And let's say that we want to factor this. So we know how to factor that. We just have to find two numbers that multiply to c but add to the middle term. So that add to b. So we need two numbers that multiply to -6 that add to be 1. How about 3 and -2, I think. How about 3 and -2? 6. 3 and -2. I'm pretty sure that's it. This ends up getting factored. It's like I'm taking this 0 equals x squared plus x minus 6. And well, if I factor that, I'm going to have x plus 3 and x minus 2. And that's the factorization of it. So that means that x equals -3 and that x equals 2. Because if we set these both equal to 0, which it is equal to 0 because of this and this, then we get two separate equations, right? X plus 3 equals 0, and x minus 2 equals 0. And well, that's the same thing as x equals -3 and x equals 2. Since we're looking at quadrant 1, right? It says the first quadrant, then we know that it's not going to be this guy here. It's going to be the positive one, right? X is positive. We're to the right of the origin. So P has to be X equals 2, right? This P has to be X equals 2. Now it's like we need to find what Q is, the intersection point here. We have to find what Q is, what's where the region ends. And so, well, Q is where the red line, x squared, intersects with the blue line, 5x plus 6. That's where the region ends. So we'll set them equal to one another, and we'll just we'll launch an investigation here, and we'll try to figure out what Q is. So let's set them equal to one another. We got 5x plus 6 equals x squared. And well, let's try to get everything onto one side. That's x squared minus 5x minus 6. And now I'll factor this by finding two numbers that multiply to negative 6 and add to negative 5. Well, I know that the answers are I know that the answers are 1 and negative 6. So so I'm going to set this up. I'm going to have what is it? It goes 0 equals x plus 1 and x minus 6, and then that's going to give me two separate equations like before. Let me try to make that better. That's going to give me two separate equations just like before. So I'll have an arrow going over here. So it's going to be 0 equals x plus 1, which is x equals negative 1, and well, 0 equals x minus 6, and that means that 6 equals x. And so, well, it can't be a negative 1. So that must mean that that x is 6. So I can set this thing up. This is gonna be the area equals this is a double integral. The first integral, we know what the bounds are for x because we're gonna do x because we're doing dy dx. So the inner integral comes first, right? So for x, we know it's going from 0 to x is equal to 2. So we're going from 0, the origin, to x equaling 2. For the second integral to the left of p, it's going to be the lower limit of integration, which is this green line, and the green line is 6 minus x, so the lower limit is going to be 6 minus x. The upper limit of integration, it's going to be right here, so it's going to be 5x plus 6. So it's going to be like right there. So this is going to be 5x plus 6, I think. And then, well, the integrand is just going to be 1. And then we're doing dy dx plus the integral from what? So we stopped at 2. This was our stopping point. We went from 0 to 2, 0 to 2. Now we're going from 2 to 6. This is not drawn to scale, by the way. But now we're going to from 2 to 6, right? Because we're trying to integrate this no, we're not. Wait, yeah. So now we're going from 2 to 6. So we're going from 2 to 6 for our x for dx. And as for the second one, remember, we're looking from the right of the point P. And so at the lower limit of integration, it's x squared. It's the red line. Lower limit is x squared, and the upper, and that's the lower limit, but the upper limit is 5x plus 6. Integral of 1 dy dx. And so that's the setup for this thing. Right here, this is the setup. Okay, come on. There we are. This is the setup for the integral. Okay, so I'm taking this I'm bringing it over here because now we have to evaluate it. Uh, so how do we want to do this thing? Well, it's kind of this first part is made a little bit easier, which of course, I mean, I say that like it's subjective, but um, well, I'm saying that because the integrand is 1. So if the integrand is 1, dy, I'm just going to tack a y onto this 1. And so now it's the integral of 1. Bounds of integration, well, not the integral of y. Bounds of integration, well, the lower limit of integration for over here is 6 minus x. So y equals 6 minus x. The upper limit of integration over here is 5x plus 6. So it's going to be y equals 5x plus 6. And then it's going to be dx, so integration with respect to x on this thing, plus this next integral, which is going to be from 2 to 6. And then it's the same situation. There's a 1 on the inside. There's usually a 1 on the inside of these things. There's a for the volume, but let me just say that this is going to be y. In the evaluation bar, it's going to be y equals x squared. And then for the lower limit of integration, for the upper limit of integration, it's going to be y equals 5x plus 6. And then this is going to be integration with respect to x. So now I have to evaluate these things at the fundamental with the fundamental with the with the fundamental theorem of calculus. And that's going to be, so we're going to put this in brackets here, and it's going to be the upper limit minus the lower limit. So this is going to be 5x plus 6 minus 6 minus x, and we'll just close that off and we'll deal with that in a minute, because we're going to have to add to this the integral from 2 to 6 plus, how does this go? 5x plus 5x plus 6 minus x squared. And this is going to be integration with respect to x. And well, with this thing, on inside of the integrand, there's going to be some distribution going on. So we'll have the integral from 0 to 2 of, well, 5x plus 6. Wait a second, I shouldn't put that in parentheses. So integrand is 5x plus 6 minus 6 plus x, plus the integral from 2 to 6 for 5x plus 6 minus x squared, integration with respect to x. Now let me just check my work. Okay, so now at this point, this positive 6 and this negative 6 are going to cancel within this integrand. So it's going to be the integral from 0 to 2 of 5x plus x, 5x plus x, integration with respect to x, plus the integral from 2 to 6 for, well, I'm going to put this in descending form, x squared plus 5x plus 6, and then this is going to be integration with respect to x. This thing is going to turn into, this 5x plus x, this is going to be 6x. So this should be integral from 0 to 2 for 6x, integration with respect to x, plus integral from 2 to 6 plus integral from 2 to 6. I'm going to do this. Negative x squared dx plus integral from 2 to 6 5x dx plus integral from 2 to 6 for 6 dx. At this point, I'm going to evaluate this. So 6 gets factored out. Evaluate this is going to be 6 times x squared over 2, evaluated from 0 to 2. That is evaluated from x equals 0, y equals 2, plus integral from 2 to x. So if I factored out that negative sign, it's going to become a minus. It's going to become minus power rule. X raised to the third over 3. Wait a second, dude, why would I put it y equals that? All right, so here. This is x equals 0 to x equals 2. Then I'm going to put a minus because I'm going to factor out that negative sign. This is going to be x raised to the third over 3, evaluated from x equals 2 to, honestly, should I just put these all in one? I'm going to put these all in one. I'm just going to put them all in one. I just am. I feel like that's going to be a lot more swift. So let's just do this. Plus what? Plus negative x raised to the third over 3 plus 5 times x raised to the second over 2 plus 6x. The whole thing is going to be from x equals 2 to x equals 6. Fundamental theorem of calculus. This is going to become 3x squared evaluated from 0 to 2. So the area equals 3x squared evaluated from 0 to 2 plus this whole thing. I gotta evaluate this at 6. Let's see. Plus negative 6 raised to the third power over 3 plus 5 times 6 squared over 2 plus 6 times 6. Oh yeah, this should be parentheses. Here. Minus what? Well, negative 2 raised to the third over 3 plus 5 times 2 raised to the second over 2 plus 6 times 2. Okay, I just need a moment to check my work. So I think I'm running out of room. So this is the area equals 2 times 2 is 4. 3 times 4 is 12. 12 plus 6 times 6 is 36. What's 36 times 6? No, it's not 36. 6 times 6 is 36. Okay, so for this one, it's like 6 times 6 is 36. What's 36 times 6? 30, let me see. 36 times 6. 36. 6 is so 18. 6, 11. 216 divided by 3. What's 216 divided by 3? 216 divided by 3. 72. So this is going to be plus negative 72. 6 times 6 is 36. What's 36 times 5? 36 times 5. Let me see here. $180. What's 180 divided by 2? 180 divided by 2 is 90. So we'll have plus 90 plus 6 times 6, which is 36. Okay. Minus 2 times 2 is 4 times 2 is 8. So that's negative 8 over 3. Plus 2 times 2 is 4 times 5 is 20. 20 over 2 is 10. Plus 12. So let me just check my work really quickly. Okay, so then now we're gonna have A equals 12 plus, what's 90 minus 72? 18. And then 18 plus 36 is 52. And so then here 90 minus 72 is 18. And then 18 plus 36 is 54. And so then we're going to add 54 to this. This negative, it gets distributed to here, here, and here. This is going to be plus 8 over 3 minus 10 minus 12. This is going to equal, 12 plus 54 is going to be 66. So 66 plus 8 over 3 minus 22. Well, minus 22 equals 44 plus, no, yeah, 44 plus 8 over 3. And 44 times 3 equals 44 times 3. It's 8. 12. 1. That's 12 is 13. 132. So we'll have 132 over 3 plus 8 over 3 equals 140 over 3. 140 over 3. 140 divided by 3. I don't know what 140 divided. I don't think you can divide. You can't divide 140 divided by 3. So the answer to this is going to be 140 over 3. So this is the answer. So now we'll begin our discussion on double integrals in polar coordinates. This is a textbook definition taken from Calculus by Briggs. It says, let f be continuous on the region R in the xy plane. and it can be expressed in polar coordinates as follows. That is, R, the region being described by r and theta, where r is in between a and b, and theta is in between alpha and beta, such that a and b are greater than or equal to 0, and that beta minus alpha is less than or equal to 2 pi, which is our full revolution. If this is true, then we can integrate f over r, and it's done so like this. So if we have this double integral of f of x and y, and we have our differential dA, that's equal to the integral from alpha to beta times the integral from a to b of f of r times cosine of theta and r times sine of theta, r dr d theta. You could think of this as like the pirate integral, because if you're ever to convert a rectangular double integral into a polar double integral, it's good to think like a pirate. R d theta, and that's the differential. So dA, the differential, which could be dy dx or dx dy, whatever you'd like, turns into r d theta, and that's why it's called the pirate integral. So it's good for circular regions, and it converts your expressions into polar form, and the transformations that we use here are x equals r cosine of theta and y equals r sine of theta, and so yeah. So now we want to find the volume of the solid bounded by the function f of x and y equaling 4 minus the square root of x squared plus y squared in the xy plane. So if I use my Desmos 3D calculator and I graph this, 4 minus the square root of x squared plus y squared, I get this cone. I get this cone looking thing, right? And so we're looking at this from above, and well, we could try to draw this out. Okay, so we have this cone thing, right? This is our cone. This is what the equation gives us in 3 space. And we have our z-axis, and we have our x-axis and our y-axis. And well, we want to find the volume of this thing. And so one thing to note is that this here, right? This is our this is our function f of x and y, and we know that f of x and y equals z, and so z equals 4 minus the square root of x squared plus y squared. And so we're prompted to find the volume of the solid bounded by this thing. So since the region in the xy plane is circular, that's a good indicator that we should be using polar coordinates. Like, that's a good candidate for using polar coordinates. The first thing that we notice is like, okay, there's a circle in it. All right, bet. So it's probably going to be polar coordinates. So the thing to do now is to convert this function that we have here into r's and thetas. And so we'll go back to look at this, and we'll say, well, r equals x squared plus y squared. Oh, excuse me. So we'll look at this and we'll say, okay, well, r equals the square root of x squared plus y squared, right? So so we know that r equals the square root of x squared plus y squared. And so if that's true, then we can look at our equation here, right? We can look at this 4 minus the square root of x squared plus y squared, and we could say, well, if z equals 4 minus the square root of x squared plus y squared, we could rewrite that as 4 minus r. And so if that's the case, 4 minus r, that's going to be f of r and theta. Wow, okay. Let's fix that. That's going to be f of r and theta. And so let's look at our region here. This is our region. And let's look at it in the xy plane. Well, in the xy plane, where 4 minus the square root of x squared plus y squared intersects, z at is 0, right? This we're looking at this the xy plane, and so it's like when z is 0, when the height is 0, that's our xy plane. So then we can set this equal to 0, right? So we'll take our 4 minus x squared plus y squared, and we set that equal to 0. And so what that means is that we can manipulate this in such a way where we have 4 equals the square root of x squared plus y squared, I think. So now, like, if I want to take this and try to find the radius of the circle, I'm gonna grab this and I'm gonna raise this to the power of 2, and I'm gonna grab this and I'm gonna raise this to the power of 2. And that's going to reveal something to us. That's going to reveal to us that indeed 16 equals x squared plus y squared. And so what does that mean? And so, well, what does that mean for us? That means that we're dealing, this is a Pythagorean theorem thing, so this means that we are dealing with a radius of 4. So if this is a radius of 4, then we can investigate this. We can look at this region in the xy plane. Okay. And so yeah, radius 4. So radius 4 goes from oh yeah. And so radius 4 goes from the origin 0 out to 4. And the region contains so in polar coordinates, you remember our polar coordinates, this is these are concentric circles. So that means that there would be a circle here, and that there would be a circle here, and that would be a circle here. And so this is technically speaking not the xy plane anymore, right? We just converted it to polar coordinates. And so to complete a full circle, that's 2 pi radians. A full revolution around this thing, that's 2 pi. So that means that, well, if we're looking at this thing in terms of polar coordinates, this operator r says, well, it's not an operator. This coordinate point r says, hey, what's the radius? How many concentric circles are we going out? Well, the answer to that is 4. And so this theta is saying, well, what's the angle? So what's the orientation of the angle? Like, what's going on with that? And the answer to that is 2 pi, because it's a full circle. A full revolution, since this is a circle, it's 2 pi. And so that means that a complete circle is 2 pi. And so what that means is that theta has to be between 0 and 2 pi. So to set this thing up, it's like, well, for the first one, so we're doing r dr d theta. So dr comes first. So dr comes first, and d theta comes second. So theta comes second. So what's theta? So theta is going from 0 to 2 pi. And then r, the radius, is we're going from the origin 0, 0 out to 4. So 0 out to the 4th circle. And well, the equation, we had 4 minus the square root of x squared plus y squared, but we know that the square root of x squared plus y squared is r. And so that means that it's gonna be, oh yeah, we said that right here. That means that in the integrand, it's gonna be 4 minus r. And then and so this is what we have in our integrand, and then we're gonna talk like a pirate and say r dr d theta, right? So so that's how you'd set that up. Now solving it, the first thing that we need to do is distribute the r. We just add another r in. So we're going to deal with the integrand. So these bounds of integration, the integrals, they're just going to stay the same. And so we're going to have the integral from 0 to 2 pi, and we're going to have the integral from 0 to 4, and we're going to have 4 times r minus r squared, and then that's going to be dr d theta, because we've just distributed that r effectively. So now at this point, what can we do? I'm gonna break it up because that's, I'm not trying to make it more complicated. In fact, I'm just gonna apply the linearity rule. All right, that's what I'm gonna do. You got a problem with it? Well, you know what? This is my YouTube channel, and this is my show. And we're gonna do this show how I want to do it. So, respectfully. So 4 times the definite integral from 0 to 4, with the integrand of r dr d theta, and from that we're going to subtract the integral from 0 to 4 for r squared dr d theta. Oh wait, just kidding. Why did I put the dr d theta? Okay, so this is going to be, and I should put this realistically, this should be going in some parentheses. You know what? Because it just does. And that's how it's going to be. So minus the integral from 0 to 4 r squared dr, and then on the outside of this d theta. And so with this, it's going to be a power rule situation for both these. Well, constant multiple rule for the first one, then power rule. So let's just jump right in, and we'll do 4 times r raised to the second over 2 minus r raised to the third over 3. This thing is going to be evaluated at, we just knocked out our r, so r equals 0 and r equals 4. And then d theta. So now it's like, well, I'm going to do the integral from 0 to 2 pi. And I'm going to do 4 times 4 squared over 2 minus 4 raised to the third over 3. And I'm not going to bother with that lower limit because it's 0. And we're dealing with r is being taken to the power and constants and division. So, and if it's like a cosine or sine, function inside the integrand, and I have a limit of integration of 0, then I start to pay attention. But when it's, and I mean, look, I'm always paying attention, but you know what I mean, like, because we want to keep an eye out for like cosine of 0 or something like that. But we don't have to worry about that right now. What we have to worry about is the integral from 0 to 2 pi. And inside of the integrand, that's going to be, well, 4 times 4 is 16, times 4 is 64, divided by 2 is 32. So that's going to be 32. minus 4 times 4, which is 16, times 4, which is 64, divided by 3. And I don't think that we can divide 64 by 3. 64 divided by 3. So we're just going to leave that alone right now. D theta. So what I will do is I'm going to try to make this, I'm going to see what I can do with this. 32, what's 32 times 3? What's 64 plus 32? 96? So we'll have 96 over 3 minus 64 over 3. What is that? 32, I think. D theta equals 0 to 2 pi of 32 over 3, which I also don't think is divisible by 3. 32 over 3 d theta equals, so this is going to be 32 over 3 theta evaluated at theta equals 0 and evaluated at theta equals 2 pi. Now it's like, I think this is just going to be 64 pi over 3. No, yeah, 64 pi over 3. Yeah, and so that's going to be our answer for this problem. So it's fun, you know, it's cool. Look, I mean, look at these cool like geometric shapes and awesome integrals and stuff, you know? And so let's move on. Let's try this problem. This problem says to find the volume of the solid using a double integral, and we're given this like weird sort of elongated stretch spherical thing, this like elliptical, this 3D elliptical thing, with an equation of 2 minus x squared minus y squared. In the region that's down below in the xy plane, it's like a sort of like a shadow kind of thing. The projection, if you will, is r, and that equation is z equals x squared plus y squared. So the region in the xy plane, that's circular. And if you look at this too, like this here, this part here is also circular. And so anytime you're given like a um a surface of anytime you're given a shape of 3 dimensions that has a component that is circular, it's a pretty good idea to try to think like, do I want to convert this into polar coordinates? If there is a uh, aspect about it that's circular, it's a good idea to weigh your options. Do I want to convert this into polar coordinates? Oftentimes you do when there's something circular in it. And so that's what we're trying to show here. So let's get on with the problem. Let's see what we can do. So the z on top is z equals 2 minus x squared minus y squared. And so we can try to we're going to use our transformations to change this. So let's see. The z on top that's going to be z equals 2 minus x squared minus y squared. And well, we look at this x squared minus y squared and we think to ourselves that this looks kind of familiar. We have an x squared plus y squared in this in this um in this equation here, but it's the square root of x squared plus y squared. So how can I manipulate this in such a way to where I can just have the x squared plus y squared isolated just by themselves? Well, what I could do is I could take that r, I could square it, and if I square that r, I square this on both sides, and that exponent of 2 cancels out with the index inside of the radical, and so it's going to be x squared plus, or excuse me, x squared plus y squared. So, so r squared equals x squared plus y squared. So let's go back to our problem right here. And so if that's true, then that means we can have 2 minus r squared. And so that's done and over with. That's done and over with, and we can move on to what's going on with the z on the bottom. Well, the z on the bottom is z equals x squared plus y squared. So, well, that literally just means that's if z equals x squared plus y squared, that equals r squared. So on the z-axis, we have 2 minus r squared, and from that, we're going to just subtract r squared. So the region R, it's formed by the intersection of curves. So this region here, this is formed by the intersection of curves. And if that's true, then I could just set these equations equal to one another. So I want to say that 2 minus x squared minus y squared, I want to say that that equals x equals, that equals x squared plus y squared. Okay. So then I'm gonna add x squared and y squared to both sides, and I'm gonna have a situation that's of such in that 2 equals 2x squared plus, plus 2y squared. That's 2 equals 2x squared plus 2y squared. But then if I divide both sides by 2, I'm gonna have 1 equals x squared plus y squared. Now that's a circle with a radius of 1. If that's a circle with a radius of 1, then in polar coordinates, it's gonna look like this. So that's what it's looking like. And so it's a radius of 1, and well, we know that r deals with the radius, so that means that it's going to be, r is going to be in between 0 and 1. The theta is what deals with the angle, but this is a full revolution. And a full revolution, it's 2 pi. So if it's the full revolution is 2 pi, then we're going from 0 to 2 pi, and so that means that theta is in between 0 and 2 pi. So let's set this up. How can we find the volume? V equals r dr d theta. D theta comes first in the setup because it comes last on the integral with respect to. So I guess what I'm trying to say is we're going to put the bounds of integration for theta on this one. So 0, 2 pi times the integral from, this is r's integral from 0 to 1. Inside of our integrand, what we need to do is we need to take this one here. Oh, okay. What we need to do is we need to subtract what we found on the bottom from the top. So I'm going to take this and I'm going to subtract it from this. So I'm looking at these two things and I'm going to say that on the z-axis, we have 2 minus r squared minus r squared. And that's what I'm going to put inside of my integrand. 2 minus r squared minus r squared. And then we do r dr d theta. Integral from 0 to 2 pi times the integral from 0 to 1. and I gotta deal with the integrand. I gotta, like, what's going on here? If I drop those parentheses here and here, I can see quite clearly that the integrand will become 2 minus 2 r raised to the second r dr d theta. Then it's the time for the distribution for r into the integrand. So if we do that, it's going to be integral from 0 to 2 pi times the integral from 0 to 1 times, r times 2, 2r minus 2r cubed dr d theta. So now what I'm going to do is I'm going to set this thing up. Integral from 0 to 2 pi times, brackets, 2 times integral from 0 to 1 for r dr minus 2 times the integral from 0 to 1 for r cubed dr d theta. So I just applied the linearity rule. Now I'm going to do integral from 0 to 2 pi. This is going to be 2 times the power rule. All these 2's are going to cancel because it's going to be like that. Minus 2 times, what is this? R raised to the 4th over 4. Like that. D theta. That's going to simplify as well. So integral from 0, almost forgot. This is going to be evaluated for r equals 0 to r equals 1 d theta. So then this is going to become integral from 0 to 2. What is this? R squared minus 1/2 r raised to the 4th, I'm pretty sure. The bounds of integration r equals 0, r equals 1 d theta. So pretty sure that's just going to become the integral from 0 to 2 for the integral from 0 to 2 pi. 1 minus 1/2 or 2 over 2 minus 1/2. Okay, so I'm just going to say that this is integral of 1/2 d theta, right? Because if I did 2 over 2 minus 1/2, or just 1 minus 1/2, it's just going to be 1/2. So we're doing this here, and well, if I evaluated that, I'm going to get 1/2 theta evaluated from theta equaling 0 at the lower limit and theta equaling 2 pi at the upper limit. And if that's the case, then it's going to be 1/2 times 2 pi. And those 2's are going to cancel. And so the answer for this is just going to be pi. This problem says to set up polar and rectangular double integrals for f of x and y equaling x squared plus y squared over the region R. And this is the region R. So for this one, x squared plus y squared. Oh yeah, this is okay, so for this, so this one says to set up the polar and rectangular double integrals for f of x and y equaling x squared plus y squared over the region R. That's x squared plus y squared. And this is over the region R. And so across here, this is a circle with radius 6. And if it's a circle with radius 6, well, 6 squared is 36. So x squared plus y squared equals 36. And let's see. If we're doing this in rectangular, the first thing that we're going to want to do is try to put this in terms of y. Because y, it's going to be a vertical slice. So it's going to be like that. So let's try to solve this for y. Y squared equals 36 minus x squared. And so y equals the square root, or plus or minus the square root of 36 minus x squared. But then it's like, well, we're looking in the upper region. And so, well, y is greater than or equal to 0 in R. So we're going to take the positive square root. So y equals the positive square root. 36 minus x squared. Okay, so let's do this rectangular. Let's use dy dx. Okay, so rectangular using dy dx. Rectangular using dy dx, right? So let me see. For the x-axis, it's -6 and 6 is the region of integration. For the y-axis, it's going from 0 to this, what we just pulled here. Y equals positive root 36 minus x squared. And then in the integrand, it's still x squared it's still x squared plus y squared. We could put that like this if we'd like. dy dx. So that's the setup. That's the rectangular setup. But for the polar setup, it's a bit different. The differential is r dr d theta. And we know our transformation here, that r equals the square root of x squared plus y squared. So here we look at this in the polar coordinates. So get rid of that. So that means that it's the sixth concentric circle out. So it's going from 0 to 6, right? R is going from 0 to 6. There would be like 6 concentric circles. 2, 3, 4, 5, 6. So it's a 6th concentric circle out. But for theta, well, theta is the angle And then this is only 180 degrees, also known as pi radians. So this is pi radians. This is only a half circle. So that means that theta is in between 0 and pi. And so if that's the case and we're doing r dr d theta, so that's going to be, theta is going to be right here. Theta, the integral for theta is 0 to pi. The integral for r, it's going to be 0 to 6. And well, on the inside, let's see, r equals the square root of x squared plus y squared. So r squared equals x squared plus y squared. So that means that we're going to have in the integrand r squared, right? Because that's our function that's given to us. And then we're going to talk like a pirate, r dr d theta. Of course, we're going to have to distribute that r in there though. So and so that's going to become the integral from 0 to pi times the integral from 0 to 6 r cubed dr d theta. So this is the polar setup. Right? We have our polar setup and we have our rectangular setup. And so that's the answer for this problem. So that's it. That's the end of this video. I keep forgetting to thank my viewers for watching at the end. And well, I wanted to make it a point to say thank you guys. I appreciate you guys for watching and good luck out there.